Okay, this is my introductory talk to the talk later this week on integral growth-Stark conjecture and explicit formulae for Brumer-Stark units. This is a joint work with Samit Dasgupta from Duke. So the plan for today's talk is I'll talk about Brumer's conjecture, I'll talk about Stark's conjecture, I'll tell you briefly about the equivalence between the two, and so it's called Brumer-Stark conjecture. Then I'll talk about its application to Hilbert's 12th problem. Um, and then I'll talk about the Gross-Stark conjecture and end with reformulation of Gross-Stark conjecture, which will motivate the tower of field conjecture that I'm going to talk about next week. And next week, not next week, later this week. And I'll also talk about the sketch a proof of the Gross-Stark conjecture in the second talk. Okay, so let's get into it. So the setup is the following: F is a totally real field. H is a finite abelian CM extension of F, and its Galois group is G. Okay, so I need some data fixed for such extension. So R is the set of all infinite places of F and all places of F that ramify in H. So it's the minimal set of places of F that we have to take in such a situation. We can take a larger set, but we are not going to do that today. And Q is some auxiliary prime of F of large enough residue characteristics. So what does large enough mean here? It means that if I take all roots of unity in F congruent to 1 mod Q, then that set is singleton. Only one is in there. So such a thing, of course, always exists. And the precise choice of Q is not important, not very important, as you will see. But we need it to make all the statements integral as we need them. Okay, so this is the setup. We have H over F, finite abelian CM extension with Galois group G. Okay, so what does the conjecture of Brumer say? It's a generalization of the classical theorem of Stickelberger, which gives factorization of Gauss sum. So there's there's an element which encodes L values of the extension H of the characters of G, the Galois group of H over F, and this element is called the Stickelberger element, and it's usually denoted by theta. So a priori, this theta lives in the group ring over complex numbers, but it's a deep theorem of Casarnogis and Deligne-Ribet that actually it's an element of ZG. And what's the precise description of this theta? So if you apply a character chi to this theta, so you evaluate this theta at a character chi, it spits out L value. So L value, L of chi inverse 0, and this sub R means I remove the Euler factors at primes in R. Okay, so in particular, there are no Archimedean factors here. And then I have to multiply it by this funny factor. So this is how this is what makes everything integral. Without this, I just get an element in QG. Okay, so so that's the Stickelberger element, and it's an element in ZG. So that's one ingredient for the conjecture that I'm going to state. The other ingredient is the class group. So this is slightly bigger than the usual ideal class group. So I take all the fractional ideals of H prime to Q and mod it out by principal ideals, but only those which have generators congruent to 1 mod Q. So there's the dependence on Q for both my objects, the analytic object theta and the arithmetic object class group. So the conjecture of Brumer says that this Stickelberger element theta annihilates the class group. Okay. So this is a generalization of the classical Stickelberger's theorem for cyclotomic fields or abelian extensions of Q more generally. Okay, there's a stronger version of Brumer's conjecture, and it says that the Stickelberger element actually lives in the fitting ideal of not quite the class group. So if you put class group here, then the statement is not true. So what you have to do, this V here, the check, it denotes the Pontryagin dual of the class group. So Hom from CLQH to Q mod Z, and minus here denotes the part on which complex conjugation acts by -1. So there's a typo here. I should invert 2 in this, so that the minus makes sense. So we can only make this conjecture when you invert 2. So at 2, it's not clear to us at all what the statement of the strong Brumer's conjecture is. So this should 2 should be inverted here. Sorry about the typo. Okay, and the minus. Okay, so it's called stronger form of Brumer's conjecture. So this should imply that. And the way this implies that is by noting that the fitting ideal is contained in the annihilator ideal. The minus here doesn't make much of a difference because for any even character, chi of theta is 0. So the plus part of theta annihilates anything you want it to annihilate. It's 0 anyways. And the fitting ideal is contained in the annihilator ideal, and annihilator ideal of the Pontryagin dual is same as the annihilator ideal. So the strong Brumer's conjecture implies Brumer's conjecture. Okay. Okay, so now we come to the Stark part of the Brumer-Stark conjecture. So Brumer's conjecture was formulated by Brumer in a series of lectures, and it was never published, as far as I know, in late 60s. And in the 70s, 1970s, Stark formulated a series of conjectures relating leading terms of L functions, Artin L functions to certain units. So I'm going to state a very particular special case of this. Okay, so for this I need a finite place P of F that splits completely in H. Okay, so Stark's conjecture always has places of F that split in H. So they could be finite places or Archimedean places, but now I'm taking finite place. And I denote by U all non-zero elements of H such that the W-adic norm of X is 1 for all primes of H not lying above P. Okay, all places of H not lying above P. In particular, W also runs through Archimedean places. So X is what is called an anti-unit, or complex conjugation acts as -1 on X. So U lives in the minus part in particular. Okay. So Stark's conjecture says that if I fix a place capital P over P in H, then there exists a U in capital U such that my theta Stickelberger element has this expression in terms of U. So this is an element in the group ring. This is the group element, and this is the coefficient living in Z. Okay, so this is an element in ZG, and this is what it says. Or if I put odd P sigma U as the coefficient in front of sigma inverse, I get my Stickelberger element. Okay, so this conjecture gives a a very nice formula for odd of sigma u in terms of the partial zeta functions, which I'm not going to introduce today, but or you can think of it as giving a formula in terms of L values. Okay. So that's Stark's conjecture in this setting. And a remark is that if such a U exists, then it's unique. Okay. There's a higher rank version of Stark's conjecture due to Rubin, so also known as Rubin-Stark conjecture, where instead of taking just one finite place of F, you can take R um, places of F that split completely in H. Okay. Um, Now I must say that if I tensor U by Q, then existence of such a U in U tensored Q is easy to see. That's just Dirichlet's unit theorem. Um, but in but getting the integral thing is hard. Okay, so that's the conjecture. For the higher rank case, you would think that U tensored Q would suffice. Yeah, so wedge power of U, rth wedge power of U would be the natural guess, but that doesn't work. So there's some subtlety, and you have to allow certain denominators, and the precise place where this higher rank analog of U lives is called Rubin's lattice. So I don't want to get into this technicality, so I'll not state the precise version of Rubin-Stark conjecture today. Okay. All right. So Tate put these two conjectures together and called it Brumer-Stark conjecture. So Brumer's conjecture is equivalent to Stark's conjecture. So it's just one conjecture basically. And let me briefly sketch how you go from Brumer to Stark. Um, I have a place P that splits completely in H, and I have fixed a prime capital P above P in H. Okay, so I look at the class of this capital P inside my class group that appears in the in Brumer's conjecture, and this is annihilated by the Stickelberger element. Okay, so I hit it with the Stickelberger element. I get a principal ideal out of it. And this principal ideal is congruent to 1 mod Q. Oh, sorry, I forgot to write 1 mod Q here. So these are all the elements. That's what gives the uniqueness. Sorry. So if you know the odd everywhere, you know it up to root of unity, and and you want to kill root of unity. Sorry. So this is important. U should be 1 mod Q. I'll make these corrections before I send in the slides. Okay, so this U will be congruent to 1 mod Q. So this is the unit that we seek in Stark's conjecture. Okay. So that's how one goes from Brumer to Stark. And the converse, you have to put together Stark's conjecture in several cases to go back. So for varying P, uh, you have to apply Stark's conjecture to go to Brumer's conjecture. Okay. Now, so a remark is that I said there is a higher rank version of Stark's conjecture, Rubin-Stark conjecture. But the higher rank version is not implied by Brumer's conjecture, but rather you need the stronger version of Brumer's conjecture with the fitting ideals. So surprisingly, this is something that the precise form is not there in the literature, but it's there in the new paper I have with Samit. Okay, so here's the theorem. So I'm not going to talk much about this theorem at all. So, but here's the theorem. So for an odd prime P, the Stickelberger element lives inside the fitting ideal like this. Okay, so here I'm considering fitting ideal over ZPG. So the statement with two inverted that I stated, the strong Brumer's conjecture, it can be proven. It can be decomposed into a statement over ZPG for each prime P, and so we prove it for each odd prime P. Okay. So again, to recall, we don't even have a statement when P is equal to 2. So it's not clear what the statement is. All right. So the one of the theorems is that the strong form of Brumer's conjecture holds. Okay. So Brumer-Stark conjecture holds away from 2. Okay, so what's the application to Hilbert's 12th problem? Well, first let me briefly recall what Hilbert's 12th problem is. So this is also known as explicit class field theory, and it, roughly speaking, asks for a construction of the maximal abelian extension of a number field in terms of data which is completely intrinsic to the number field. So you want an explicit construction of FAB and not just some information. So class field theory tells you that the Galois group of FAB over F is in terms of the data intrinsic to F, but we want actual construction of FAB. So the first example is Kronecker-Weber theorem, which of course dates back to before Hilbert stated his 12th problem. So Q ab, the maximal abelian extension of Q, is generated by the values of the exponential function e to the 2 pi I x at rational numbers x, so x equal to 1 by n. So this is what this is an example of explicit class field theory, and there's a theorem over imaginary quadratic fields. So those are generated by values of j function at torsion points of elliptic curve and Weber functions. I'm not going to state that. Okay, so what is the significance of Brumer-Stark conjecture for Hilbert's 12th problem? Well, so if I fix an integral ideal f of my totally real field capital F, I take a prime P of F, which does not divide F, so it's co-prime to F, and let HF comma P be the maximal abelian CM extension of F. This conductor divides F and in which P splits completely. Okay, so HFP is a finite extension of F. And I have the Brumer-Stark unit in this setting. So maybe the script P has odd residue characteristics to make everything unconditional based on the new theorem I stated. And UF comma P is the Brumer-Stark unit in this setting. And one can show using the Brumer part of the conjecture that UF comma P generates this maximal abelian CM extension of F with conductor dividing F, and in which prime P splits completely. Okay, so this unit generates this extension. So which means that HF comma P is F, and then you adjoin this U to it. Okay, so so as I vary my integral ideal F and as I vary my prime P overall but finitely many primes of F, for example, so that everything is unconditional, I get, well, I don't quite get the maximal abelian extension of F. I get the maximal abelian CM extension of F, and then I have to adjoin some roots of square roots of some number, so numbers in F. So these are the set of elements in F whose signs in this set form a Z mod 2 Z basis. So the dimension Z mod 2 dimension of this set is D minus 1, and I have to pick these elements and apply and take square roots of it. So I have to adjoin that. So that gives me the maximal abelian extension of F. Okay. So all right. Okay. So to get the maximal abelian extension of F, I take these Brumer-Stark units and I join them. Okay, so Brumer-Stark conjecture tells me that these things are uniquely determined, but it doesn't tell me anything about how to construct it. So this is an element of H, and I can look at its image in H completed at capital P, which is same as F completed at capital P. So I can ask what this element is as an element in this field F, this local field FP. Is there a formula for this so that I can write down this element completely? The Brumer-Stark conjecture doesn't tell me anything about this. Okay, so but if there is a formula for this, then that will give us a solution to Hilbert's 12th problem. Okay, so this was motivation to Samit's study into these units, to these Brumer-Stark units, and he made uh, he made a conjecture about this. So firstly with Darmo, when F is a real quadratic field, and then later for any totally real field, and lastly with Spies for the higher rank version. Okay, so analog in the higher rank version. Okay, but before that, there are a couple of conjectures of Gross. So the Gross-Stark conjecture and the Tower of Fields conjecture, which was again made by Gross a few years after he made the Gross-Stark conjecture, which give you more information about this Brumer-Stark unit. Okay, so but it still doesn't determine it completely. So this we'll see today, and in the next talk, what exact information does the Gross-Stark conjecture and the Tower of Field conjecture give about the Brumer-Stark unit. But remarkably, Dasgupta and generally Dasgupta and Spies gave an explicit formula for the Brumer-Stark units, okay, and also their higher rank analogs, so the Rubin-Stark elements or the Brumer-Rubin-Stark elements as they are called, in terms of what are called the Eisenstein co-cycles. So the Eisenstein co-cycles have been studied by many people, um, Czech and Dasgupta and Charlois, with Matt Greenberg and Williamson, uh, Levine and Kings, and so on. So there's a long list of people who have studied this from different points of view. But I'm not going to talk about these Eisenstein co-cycles. These are analytic objects, and uh, Dasgupta and Spies give an explicit formula for Brumer-Stark units in terms of Eisenstein co-cycles. Okay, and you can actually use these formulas to compute the Brumer-Stark units explicitly. So there are lots of examples on Samit's webpage that one can look at. Okay. A special case when P is inert in F, um, we can write this. We can write down a nice integral expression for this. So sigma is an element of the Galois group. So and for a so we can write down a formula for every conjugate of U. So that's how we find the minimal polynomial of U. Okay, so this is given by some integral, multiplicative integral, with respect to some measure. So this measure is constructed out of Eisenstein co-cycle, or in this special case using Shintani's formula. Okay, and there's some error term here which is given by the value of the partial zeta function. Okay, so this is the term that appears from Brumer's conjecture. Okay, and then this is some other part of it. So this remarkable formula tells you that give helps you to write to determine this u explicitly. Okay, so this conjecture, this Gupta's peace conjecture, can be thought of as a p-adic resolution of Hilbert's 12th problem for F. Okay, so that's the significance of Brumer-Stark units. That Brumer-Stark units, along with these explicit formulae uh, that we have, it gives a p-adic resolution of Hilbert's 12th problem. So what's our way into Dasgupta's conjecture? Um, so in the next talk, I'll sketch how one deduces Dasgupta's conjecture from the Tower of Fields conjecture of Gross. So I said that Gross's conjecture doesn't give you um, you explicitly. It doesn't determine it entirely, but it sort of determines it enough so that you can put lots of cases of Gross's conjecture together um, with choices of auxiliary primes, as we'll see next time, and we deduce this conjecture of Dasgupta. So our way into these explicit formula is through Tower of Fields conjecture. And the Gross-Stark conjecture is a special case of Tower of Fields conjecture. So the plan for the rest of this talk is to give formulation of the Gross-Stark conjecture as it was first stated, and then give a reformulation which will motivate the Tower of Fields conjecture that we'll see next time. Okay, so here's the statement of the Gross-Stark conjecture. I take a first we need first I need to introduce the p-adic L function. So again, let chi be an odd character of our Galois group of H over F. Then to such a chi, we can attach a p-adic analytic function, which I denote by LP chi omega S. This is analytic on ZP minus 1, so everywhere except at S equal to 1. And it has this interpolation property. Okay, so this is the p-adic L function of Cassel-Nogues and Deligne-Ribet. What's the interpolation property? If I put S equal to any negative, non-positive integer, I get the usual L value of chi to the omega to the n. Omega is the p-adic tachymular character here. At this non-positive integer n, so I get this L value out of it. And these L values are all non-zero because chi is odd, omega is odd. So if n is odd negative, this is an even character, and I have even character, L function of even character at odd negative integers, that's non-zero, and L function of odd character at even non-positive integers, so that's non-zero. So these are all non-zero numbers. Well, I don't quite get this. To get the p-adic analytic behavior, I have to multiply it by Euler factors at P. So I have to remove Euler factors at P. So I have to multiply by the reciprocals of Euler factors at P. Okay, so the existence of this was proven by Cassel-Nogues and Deligne-Ribet independently. Okay, what about S equal to 1? Well, this is regular at S equal to 1, except possibly when chi is omega inverse. Okay, so well, at the trivial character, it's supposed to have a pole, and that's Leopold's conjecture. So that's why, because we don't know Leopold's conjecture, so it may not be not have a pole. Okay, so it's regular at S equal to 1, except when chi is omega square. Okay, so it is easy to see that if chi of p is 1 for some prime p dividing the prime number p, then L chi omega at 0 is 0, because one of these factors that you're multiplying by is 0. Okay, so such a 0 is called trivial 0. Now, an obvious question is, what happens if, all, for instance, all of these primes dividing, for all of these primes p dividing p, chi of p is 1. What happens then? Well, this formula doesn't give us anything about whether LP vanishes to higher order, but Gross conjectured that, and Kuzmin conjectured independently something slightly different, and those two statements are equivalent. Um, so here's the conjecture. Let R be the number of primes above P that for which chi of P is 1. Then Gross conjectures that the order of the p-adical function at s equal to 0 is precisely R. Okay, so that's Gross-Kuzmin conjecture. So what's known about this conjecture? So here's the conjecture stated again. Well, Wiles, this follows from Wiles's proof of the main conjecture that odd of L, the order of vanishing of the p-adical function at s equal to 0 is at least R. Okay, because for the Selmer module we can show that so we can show that the order of vanishing of the characteristic element is at least R by some explicit construction. So once you know main conjecture, we know this. So there seems to be some issue at p equal to 2. So this works only for p bigger than 2. Well, there's a purely p-adic analytic proof of this fact due to Dasgupta and Spies, again using their Eisenstein co-cycles. They show that this the order of vanishing is at least R, and it works without any change at p equal to 2 as well. Okay. The equality is seems to be a hard problem in transcendence theory. So similar to Leopold conjecture. So there's similar to Leopold regulator, there's Gross regulator, and the equality would hold if one can show that this Gross regulator is non-zero. Well, but for R equal to 1, we know it's true. And again, this uses a hard p-adic transcendence theorem due to Baker-Brumer. Okay, so it uses the Baker-Brumer theorem about linear independence of logs of algebraic numbers. All right, but nevertheless, this Gross-Kuzmin conjecture is known when R is 1. Okay, so coming back to our Gross-Stark conjecture, well, now we know that the order of vanishing is at least R. We know that the first R minus 1 derivatives are 0, and the first possible non-zero derivative is Rth derivative. Okay, so the Gross-Stark conjecture gives a formula for the Rth derivative in terms of Gross regulator that I'm going to define now. So I give my set a name. This is S, and I enumerate this P1 to PR. And I put U. So this is a slightly different thing, but than before. But it's consistent. Okay, so U is I take all P units and I take the chi inverse part of it. Okay, so I tensor it with E, where E is some sufficiently large extension of QP, and then I take the chi inverse component, isotypic component of this. Then Dirichlet's unit theorem, or rather some Galois equivariant version of Dirichlet's unit theorem, tells me that the dimension of U over E is precisely R. So this R here. So I can fix an E basis of U and call it U1 up to UR. And for each of these PIs, I fix capital PI of H above P. Then this is the statement of Gross-Stark conjecture, that the rth derivative, suitably normalized, so I take it to divide it by R factorial because I want the leading term. And then I have removed a lot of Euler factors, so maybe I put many of them back. I mean, all but whenever this is non-zero back. Um, and I take the complex L value of chi at s equal to 1, this side is equal to the gross regulator, so this determinant. Okay, so I take norm from f of pi to qp. Recall that this u lies in h, so uj, so this uj lies in h, which means I can look, I can complete h at capital Pi, so it lies in h sub pi, which is same as f sub pi. So this uj lies in f sub pi. I take norm from f sub pi to qp, and then I take the periodic, the Iwasawa logarithm of this, so Iwasawa periodic logarithm of this. And I do this for all j from 1 to r, and I do this for all I from 1 to r. I get an r by r matrix. I take its determinant. So this numerator is what is called the gross regulator usually, uh, or this ratio, whichever, depending on how you want to normalize it. And in the bottom, I have to take odd with respect to this capital Pi. Okay, this denominator is non-zero because this is a basis of u. All right, so in the special case when r is 1, for example, this conjecture, this statement gives a formula for norm of u in terms of the leading term of periodical function. Okay. All right, so what's known about this? Well, this conjecture is basically completely known. So the Brumer-Stark conjecture holds, which means that this formula holds. This is just the formula copied from the previous page. Okay, so this formula holds, and in general, so this was proven when r equal to 1 by Dasgupta, Darmo, and Pollock, with some conditions which were later removed by Ventilo, and then the general case for r bigger than 1 was proven uh, uh, with Dasgupta and Ventilo. Okay. So when r is equal to 1, we know that this is non-zero, but when r is bigger than 1, this side may be 0, and the content of the theorem is that this side is also 0. Okay, so we don't assume Gross-Kuzmin here. Of course, if Gross-Kuzmin were true, then both sides would be non-zero, but otherwise we have to prove that 0 is equal to 0. Okay, so I'll end this talk with a reformulation of the Gross-Stark conjecture, which is now a theorem, in terms of the sort of in a way that motivates the Tower of Fields conjecture naturally. Okay, and in the next talk, I'll give the Tower of Fields conjecture, sketch how it implies Dasgupta's conjecture, and then sketch a proof of Tower of Field conjecture, but only through this example of Gross-Stark conjecture. Okay, so not in general, but it will be kind of clear that whatever I'm doing for this reformulated Gross-Stark conjecture should, work with some work for also the Tower of Fields conjecture. Okay, so how do we reformulate this? Well, I need a Tower of Fields for this conjecture to that's what the name is, towers of field conjecture. So this is the tower I take. I take the cyclotomic ZP extension of H. Okay, so Galois group of H cyclotomic over H, which I call gamma, is isomorphic to ZP. So I have this tower H cyclotomic over H over F. Okay. Then for every Pi in S, there's the Artin reciprocity map, which goes from F sub Pi star into this Galois group. Okay, so it goes into the decomposition group, but then I can put the decomposition group into gamma, and then this is a subgroup of Galois group of H cyclotomic over F. Okay, so recall that chi is an odd character and of G. And I have this. Okay. I put O to be the ring obtained by adjoining values of chi to ZP. Um, so I have to work in this Iwasawa algebra of gamma with coefficients in O. And for those who may have not seen it before, this is simply isomorphic to the power series ring in one variable over O. Well, this isomorphism is not canonical unless we fix a topological generator of gamma. But this just helps visualize what kind of ring this is and what kind of ideal we'll be dealing with later on. So what kind of ideal this augmentation ideal is. So there's the augmentation map from the Iwasawa algebra to O. It just sends all the elements of gamma to 1. So that gives me a ring homomorphism from O gamma to O. And I take kernel of this homomorphism. This is called the augmentation ideal. And it's simply isomorphic to the ideal T if you fix this isomorphism. Okay, and in this case of Brumer-Stark, so when gamma is ZP, the graded pieces with respect to augmentation are also very nice to understand. So this kind of things are very complicated, even uh, for Z when if gamma, instead of being a nice pro-cyclic or cyclic group, if it's Z mod P cross Z mod P, these things are horrible. So as we'll see next time. But here it's nice. So if I take I to the S mod I to the S plus 1, this is simply isomorphic to gamma, which is isomorphic to ZP. Okay. So okay, so what is the image of so this is an element of gamma. I subtract 1 from it, so it lives in I. Okay, and if I look at its image um, in I mod I squared, so S should be 1 for this statement. If I look at its image in I mod I square, this is simply a p-adic log of norm of U. Okay, so this is the kind of thing that appeared in Gross's regulator. Okay, because how is the reciprocity map defined in this case? Yeah, it's quite explicit. You take norm of any element from this down to QP, and then you take p-adic log of that. So that lands inside ZP, and you use that gamma is isomorphic to ZP. Okay, so so the element in this element in I mod I squared is simply this log. Okay. All right. So this is one side of Gross-Stark. What's the other side? The other side is the p-adic L function, and we can get the p-adic L function out of these Stickelberger elements. Okay. So we have the Stickelberger element for finite extension H over F, but we can also have it for an infinite extension H cyclotomic over F, because they all behave well in a tower, and so we can take the there's inverse system, and that lives inside um, Gal the Iwasawa algebra of Galois group of H cyclotomic over F, and then I apply this character chi to it to get an element in this Galois group. Okay. All right. So there's this map from this into this, which is obtained by applying chi to any element in here, or inflation of chi, and then also taking the image of that element into gamma. So here I look at gamma as as the Galois group of F cyclotomic over F. So I'll not explain this in detail. Anyway, you can get an element in here by applying chi. Okay, then this result of Dasgupta and Spies that I mentioned, or a slight generalization of this implies that this element actually belongs to augmentation ideal to the R. Okay, so it's divisible by t to the r if you use this isomorphism between I and t. This is precisely saying that the order of vanishing of the p-adical function is at least r. Okay, and what is its image under this isomorphism from I to the r mod I to the r plus 1 to this? So it almost gives you the leading term of the p-adical function. Okay, but we have to multiply it by this factor which makes everything integral. Okay, so this auxiliary choice of q comes into place. Okay. All right. So the reformulation of the Gross-Stark conjecture is that well, I'll only state it in r equal to 1 because in the original formulation of the Gross-Stark conjecture, we did not have to assume Brumer-Stark conjecture. Well, again, here we don't really have to assume it, but since we know Brumer-Stark conjecture now, I'll assume it and state it in the nicer form that it can be when you assume Brumer-Stark conjecture. Um, so if I want to state it for r bigger than 1, I have to also recall the Rubin Brumer-Stark conjecture or Rubin-Stark conjecture, which I don't want to do. So I'll just state it when r is equal to 1 for now. Okay, so what it says is that if U is the Rubin-Stark unit, the Brumer-Stark unit, then this element as an element in I mod I square is also equal to this element. Okay, so reciprocity applied to all these conjugates of Rubin-Stark units minus 1. So this is an element in I have to normalize it with chi sigma inverse and take this summation. So this thing as an element in I mod I square is also equal to this as an element in I mod I square. Okay, so that's the reformulation of Gross-Stark conjecture. So now if you replace this H cyclotomic over H by any extension L over H with some mild conditions like unramified outside finitely many primes and so for instance, even if you just take finite things, so that's okay. So if you replace this, you can make sense of everything. So there's the reciprocity map, there's the augmentation ideal. It may not have a simple form like this. It won't have some nice description like this, but some power of augmentation ideal modulo the next power that makes sense. This will live in I, and the generalization of Dasgupta's peace theorem will tell you that this thing lives in I to the R, and so one can formulate a conjecture which looks just like this in I mod I square, or if R is bigger than 1, then I to the R mod I to the R plus 1. So that's going to be the tower of field conjecture. Okay. So that's it. And in the next talk, in the main talk, I'll introduce the tower of field conjecture and then sketch a proof of it. So that's the new result. Okay.